Okay, hi everybody. We're reuniting again and we're going to continue on with the beginning of chapter 9 and the conclusion of 9.1. Now, the title of 9.1 is Finding Roots. And this last section that we're going to be taking a look at is primarily dealing with finding roots. Now, as we continue to move through chapter 9, the major theme that we're going to be looking at is radicals have certain rules that we have to follow. There are certain rules that are set up when we are simplifying radicals that we must abide by. And today, at the conclusion of 9.1, as we move into this last section, we're going to be taking a look at the first rule of simplifying radicals. And here's that first rule. If a radical expression represents a rational number, we write the rational number in place of the radical. Now let me say that again as I point to this very elementary radical expression. The radical of 81. Now let me headline this rule again. If the radical expression represents a rational number, well, from what we've already talked about, we know that this radical expression represents a rational number because the radicand of 81 is a perfect square. And if the radicand is a perfect square, its root will always be a rational number. So rule number 1 is saying this: if a radical expression represents a rational number, we write the rational number down in place of the radical. And folks, that's common sense. We're not going to leave this problem written as the form of the radical of 81 when we know its positive square root is 9. And 9 is a rational number. So we would simply write down 9. We're not going to leave it the radical of 81 when 81 is a perfect square. We're going to write down its rational root. So in the problems that we're going to be looking at now that will complete 9.1, they are all, for the most part, going to follow Rule 1. If a radical expression represents a rational number, we're going to write the rational number in place of the radical expression, or instead of the radical expression. Now, there's going to be 2 different categories that are going to follow this rule. The first category is if the index of the radical expression is even. When we get to letter B, it will be if the index of the radical is odd. So the first set of problems that we're going to look at for this rule number 1 is simplifying or evaluating radicals when the index is even. And here's the rule that will follow if the index is even. If the index of a radical expression is even, the radicand must be non-negative for a root to exist for the set of real numbers. Now, a short and sweet statement is this: if the index is even, the radicand must be non-negative for a root to exist. The radicand cannot be negative if the index is even. So we're going to take a look at a few examples, and I'm going to be putting these examples right in this area right here. I'm going to erase that rule. We've already identified it. It is on the video. The directions say, find each root if possible. We're going to start with this guy right here. The radical, and I'm going to put a negative sign on the outside. Now take a look at the index so that you know that this is following capital letter A. If the index is even, it's an index of 2 because we're finding the square root. Then that means the radicand has to be non-negative, and it's non-negative. So we're going to evaluate and find this root. Now I started off with this one to make a key point. Obviously, one thing that a student can do, is they can punch in 324 into the calculator, hit the radical button on the calculator, and I believe it will produce 18, which is the rational root for the radical of 324. But people, let's assume that we don't have the calculator. I want to generate that answer by sharing something your way that we're going to be using as we move through Chapter 9. If we don't have a calculator, and we're just not quite sure what the square root of 324 would be, we don't want to keep guessing numbers to eventually figure it out. We want to come up with a mechanism that we can use to find its square root. Now, please understand this. When you see me demonstrate this, I know some of you will look at it and say, well, I'm not going to worry about what you're doing up there. I could just use a calculator and I would get my answer. And you're right on that. But in the long run, you're going to appreciate what is going to be shared here. So I'm going to bring down that negative sign, and I'm going to bring down a brand new radical sign. And we're going to begin by taking this radicand of 324, and I'm going to write it over here to the side. And we're going to prime factor 324. Now, I don't tend to use a factor tree like many of you do. I use a method that's called upside down division. We take a division symbol and we turn it upside down. And we begin by taking the very first prime number that exists, which is the prime number of 2. And we're going to see if 2 divides into 324, and it will because 324 is even. And so we're going to begin by dividing 324 by 2, and that's going to move that down to 162. 162 is still even, so we're going to continue to divide by 2. So we just make another upside down here, put another 2 on the outside, and divide it into 162, and it'll give us 81. 81 is no longer even, so that means we can no longer use 2 to divide into that. The very next prime number after 2 is 3. 3 does divide into 81 because of its rule. If you add the digits up, the 8 added to the 1, if you add the digits up, and if that sum total that we get is evenly divisible by 3, then 3 will be a factor of 81. 8 plus 1 is 9. 3 divides into 9. 3 must divide into 81. And 3 will divide into 81 27 times. And if we divide it again by 3, it'll go 9. And if we divide it one more time by 3, it'll go 3 times. Now, these prime numbers that are on the outside of these division symbols form the prime factorization of 324. And when I write out the prime factorization of 324, I'm going to use exponents wherever I can use them. So we're going to start with our 2's. There happens to be 2 of the 2's. So I'm going to express those 2 factors of 2 as a power. And I'm going to build it in right here. We'll write 2 to the second. That takes care of those 2. I'm going to make a little time sign. We're going to amass the total number of times the 3 occurs. 1, 2, 3, 4. 3 to the 4th. Now, here's how we can as well pull out the root of 324. Let's go ahead and bring down this negative sign and get it ready. As a matter of fact, I'll even show it as a -1 because that's actually what it is. If you look at this radicand factor of 2 squared, that exponent of 2 is even. That means it's a square. To find the square root of 2 to the second, you simply do this. You bring that base down. Just bring it down. And take the exponent in that radicand and divide it by the index number. The index number is a 2 because this is square root. If we divide 2 by 2, we get 1. So that means the square root of 2 to the second would be 2 to the 2 divided by 2, which would give us 2 to the 1, or just simply 2. And we'll just leave it that way. I'll bring down a time sign. This 3 to the 4th, he is a square because 4 is even. We're going to do the same thing to this one. Bring down that base of 3. Take that exponent of 4 and divide it by the index of 2. 4 divided by 2 is 2. We'll put that exponent right there. And now let's multiply this out. -1 times 2 times 3 squared is 9. And we should get a -18, which would just happen to be the solution of that radical expression. Now, I know what you would be saying. Hey, Kent, I would have had that answer 10 minutes ago. And yes, you would have. But again, you're going to see the importance of prime factorization as we move further along in the course. I wanted to share it. That's why I included that as one of those examples. Now let's quickly move on. The only reason why I used prime factorization whatsoever was because of the size of that radicand. If it's not necessary, then it isn't necessary. But there are times when we want to have that. Now real quickly, number 2. Let's just go to this one right here and go through these. A different looking radical expression. Don't make this mistake. Don't find the square root of 9 and then follow that up by finding the square root of 25 and then taking those 2 separate answers that you get and subtract them from one another. That radical sign is also a grouping device. You bring down that radical sign and you do the operation inside underneath that radical. 9 minus 25. Positive 9 combined with a -25. Really subtract. Take the sign of the bigger absolute. And then look at the radical expression. There is no root that can exist for this one. That's why the directions said, find each root if possible. It is not possible to find a root for this in the set of real numbers because the radicand is negative. It's not non-negative, it's negative. It can't be 4. It can't be -4 because the radicand is negative. So you simply write down no real number root. Don't write down the answer is 0. Don't write down that it doesn't exist. Don't write down undefined or no solution. It is no real number root. All right. Next, quick one, just to share. Index is 2. Its square root. The radicand is non-negative. We can evaluate it. We can find its root. The numerator, it's a perfect square. The denominator is a perfect square. We'll just pull it out. If the radical expression represents a rational number, and he does, we write the rational number in place of the radical. 9/10. Put it to bed. It's done. It's done. Don't do anything more with it. It's done. We could have only reduced if it was able to be reduced, but it can't be reduced. All right? Number 4. I'll put a negative sign out here. 0.001296. Now, for the sake of time, I'm not going to be doing any prime factorization for this one because that's not the emphasis of the key item that I want to discuss. Obviously, we look at the radical. The radicand is non-negative. It happens to be a decimal fraction. It's a decimal. And we're going to make an assumption that the non-zero portion of this radicand, the 1296, we're going to make an assumption that it represents a perfect square, and it does. The point is, how would we do this one if for some reason we didn't have, well, if we didn't have the calculator right at our disposal right away? We want to share a key rule that you would have seen in your Math 50 course. That negative sign on the outside is going to be part of the answer. We're going to bring it up. And we're going to take that decimal point that you see in that radicand, and we're going to move it straight up. Now here's the rule. If this radical expression represents a rational number, we're going to write the rational number in place of the radical expression, and it will equal a rational number. But here's the rule that we need to be aware of when we are evaluating a root that happens to be a decimal. The only way that this radicand can represent a rational number if some conditions hold. Here's one of those conditions. If you count the number of digits to the right of the decimal point, there's the point. If you count the number of digits to the right, the number of digits to the right of that decimal point must be an even amount. It must be an even amount. 1, 2, 3, 4, 5, 6. There's an even number of digits to the right of that decimal point. That will indicate that if 1,296, this portion right here, happens to be a perfect square, because there is an even number of digits to the right of that point, it will represent a perfect square and give us a rational number up here. How many digits will there then be in our answer? Well, that's the second thing that we want to say. First of all, there has to be an even count to the right of the point, and there are. There were 6. How many digits will there be in our answer? To determine that, take the even number of digits in our radicand and cut it in half. Divide it by 2. Well, there's 1, 2, 3, 4, 5, 6. 6 divided by 2 is 3. That means there's going to have to be a total of 3 digits in our answer to the right of the point. If you punch in 1296 into your calculator, it will show you that the square root of 1296 is 36, I believe. 36 is made up of 2 digits. The 36 will fulfill the last 2 squares. You'll prefix your answer with a 0. And your answer will be a negative 36 thousandths. Don't forget the negative. And that would be that situation right there. Yes, the calculator will do it. It will do it. Am I okay, or do you want to? All right, let's go ahead and continue on with the section where the index is even. Now, the first few problems that we were looking at, as you view what we had done, the radicands were all numerical values. And now beginning with number 5, we're looking at a radicand that has a variable expression in it. But number 1 item, when you're looking at a variable expression that has the given exponent in place, if that exponent is even, then we know that that variable expression as well represents a perfect square, and therefore this radical expression would represent a rational number, and we're going to write the rational number in place of that radical. But there is something very important that needs to be mentioned as we take a look at a problem like number 5, and I want to deal with it as carefully as I can. We begin off by recognizing the fact that our index is a 2 because it's square root. We're going to take that base of that exponential expression in underneath that radical sign, and we're going to bring that base down. If we take its related exponent, 2, and divide it by the index of 2, 2 divided by 2 would give us 1. Therefore, on the surface, it appears that the radical of n squared and its root is simply n, because n to the 1 is the same thing as n. But folks, here's the situation that I want to introduce you to for just a moment. The definition of a variable says that a variable can vary in sign. A variable can represent any number. It can represent a positive number, it can represent 0, and it can represent a negative number. So the value of this answer of n can be negative according to the definition of a variable. But if we come back up here to the original problem, it's underneath that radical sign. It's a square root situation. And remember, the definition of that radical sign is the positive square root of. That means the answer has to be positive. But now go back down here and look at this variable of n. The definition of a variable says it can represent any number. It can represent a negative value. But we can't let this represent a negative value because the problem was below that radical sign, which is defined as the positive square root. So how would we handle this situation if a direction says that n can be any number? Then that would mean n could be a negative number. But it can't be negative because of that radical sign there. So to make both of these rules satisfy, meaning to allow n to be a negative number, but yet make sure that our overall answer is not negative, we'd have to do the following. We'd have to take that answer of n and we would have to put it in between an absolute value symbol. Now let's just check this for a second. Let's say n is a negative 1. or -2, or -3, or -4, or any negative number. You can let it be any negative number as long as it's in between the absolute value symbols, because remember, the absolute value of any number is always positive. So even though the value of n might end up to be a negative number, if it's placed in between the absolute value symbol, then our final answer will be positive. And both of those considerations that we were talking about then would be happy. They would be they'd be satisfied by that. Now, I'm going to give you a heads up on this as we move forward with this. In our class of Math 51, as well as Math 71, I've identified the rule, so to speak. But from this point on, we're not going to worry about the use of the absolute value symbol, because we're going to make a rule. And the rule will be the value of the variable in the radicand position will not ever be able to be equivalent to a negative number. We will not let it be negative. We will point that rule out to you so that we won't have to worry about absolute value. But I wanted to give you that rule because you're going to be faced with it very likely down the road. I'm also going to give you a statement as to let you know when an absolute value symbol would have to be used and when you wouldn't have to worry about using it whatsoever. But let's just review that. If I bring down that n and we take that exponent and divide it by the index, I get n, or n to the 1. Would you just kind of be mindful of the fact, let me just kind of put that 1 there for a second, okay? I want you to notice that that little exponent right there is odd. Let's go to number 6. If I bring down the y and take the exponent of 10 and divide it by the index of 2, 10 divided by 2 is 5. Therefore, he represents a rational number. The root of y to the 10th would be y to the 5th. Notice, I already told you we're not going to have to worry about absolute value, but I do want to promote the rule in terms of how do we know when an absolute value device would have to be used and when it wouldn't have to be used. Let's make up a value for y, and let's make it a negative number. Let's say y is a -1, just for purposes of discussion. If you were to take -1 and take it to the 5th power, -1 to the 5th power would be -1 times -1 times -1 times -1 times -1, which would give us an answer of -1. Our answer can't be -1. It can't when it's underneath that radical sign. So we would have to use an absolute value around this one as well, if we were going to enforce that rule. Now, we're not going to enforce it, but I enforced it for a moment so I could promote a rule. Here's the rule. Notice the exponent of our root answer was odd. Notice back on number 5, the exponent on our root answer was odd. Here's the rule. If the radicand is a variable expression and it represents a rational number, if the root, once you have determined the root, if the exponent on your root answer is odd, you would ordinarily need to use an absolute value symbol. You would ordinarily have to use one. Now, we're not going to enforce that rule, but that is the rule. If the exponent on your root answer is even, which I'm going to show you in the next example, absolute value would definitively never have to be used. But it would ordinarily have to be used on number 6 because that exponent is odd, and it would have to be used on number 5 because that exponent is odd. But I've already told you we're not going to have to worry about that. So as far as I'm concerned, the answers for 5 and 6 would simply be n and y to the 5th. We're not going to worry about the absolute value device. But later on, you will. Later on, you will. Now let me go to number 7 and promote the one where you would not have to worry about it. That represents a rational number because the power in the radicand has an even exponent. Bring down the x. Take the exponent of 8, divide it by the index of 2. 8 divided by 2 would give us x to the 4th. Now let's just consider this and see if absolute value would really have to be used. Let's let x be a negative number again. Let it be negative 1 again. If x is negative 1 and you take that to the 4th power, notice the answer that you'll get when you take negative 1 to the 4th. Negative 1 times negative 1 times negative 1 times negative 1, that would be a positive 1. The answer cannot be negative, and it would not be negative in this case. And it never will be if the exponent on your root answer is even. So on this one, you wouldn't need an absolute value device. It would just remain x to the 4th. But to repeat myself one more time, we're not going to use absolute value whatsoever. Now, 8 and 9 will go roughly pretty fast right here. Number 8. The radical of 64. X to the 14th, y to the 6th. Now I'm finished talking about absolute value. So here we go. 64 is a square. Our index is 2 again. X to the 14th is a square because 14 is even. Y to the 6th is a square because 6 is even. Let's just bring the thing down. Start with the radical of 64. No issue. 8. Bring down your x. Take the exponent of 14 and divide it by the index of 2. 14 divided by 2, x to the 7th. Bring down the y. Exponent of 6 divided by index of 2. 6 divided by 2, 3. Y cubed. Done. Done. Now, in actuality, if absolute value was enforced, you would need an absolute value around the x to the 7th and around the y to the 3rd because both of those exponents in the root answer are odd. But we're not going to worry about it. It's not that important. Okay? All right. One more similar to that, just so that you have it. I'm going to put a negative sign there on the outside. The radical of 4. M squared. N to the 18th. T to the 20th. Look at your index. It's even. It's 2. Bring him down. The radical of 4. 2. Bring down the m. Take its exponent, divide it by the index of 2. 2 divided by 2, m to the 1, or simply m. Bring down n. 18 divided by 2, n to the 9th. Bring down the t. 20 divided by 2 to the 10th. Little guy's done. Now it's going to change to another index. The 4th root of 81. Now here is where I believe that prime factorization will pay off. because even a calculator won't necessarily help somebody figure out if 81 represents a perfect fourth power. Not a perfect square, because our index is no longer 2. We need to determine if 81 happens to be a perfect fourth power. And if it is, then it represents a rational number, and we're going to write that rational number down. Now, we're going to do prime factorization for this because it will help us see very nicely that this 81 is a perfect fourth power. So I'm going to get this thing ready right here. Take 81 and pull it out here. We're going to do an upside down division for 81. We can't use 2 because 81 is odd. But we can go to the next prime number in 3, and we can use 3 because 8 plus 1 is 9. Outside, it'll go 27 times. Again by 3, it'll go 9. Again by 3, and it'll go 3. 1, 2, 3, 4. 3 to the 4th. Yes, it's a perfect fourth power because the exponent on that base of 3 is 4. 4 is evenly divisible by the index. Bring down your 3. Divide that 4 by the index of 4. You'll get 3 to the 1, or simply 3. The fourth root of 81 does represent a rational number because our root answer is 3. I believe that's a key item to use. I really do. One more. One more in this A section of even index. Number 11. The sixth root of 64, n to the 6th, t to the 18th. Well, now there's no doubt about it. This n to the 6th is a perfect 6th power because its exponent is evenly divisible by its index. T to the 18th is a perfect 6th power because its exponent of 18 is evenly divisible by the exponent. The question is 64. But if we use prime factorization, we'll find out if 64 is a perfect 6th power. I'm going to get it ready. And I'm going to squeeze that 64 right here. Folks, it's even. We'll do it by 2. 2 goes into 64 32 times. Again by 2. It'll go 16 times. By 2, it'll go 8 times. By 2, it'll go 4. By 2, and it'll go twice. Count them. 1, 2, 3, 4, 5, 6. That exponent is evenly divisible by that index. Let me bring down that n to the 6th and that t to the 18th. And now let's get it out of the house, because that radicand represents in totality a perfect 6th power. Bring down the base of 2, divide 6 by 6. That's 2 to the 1st, or simply 2. Bring down the base of n. 6 divided by 6 is 1. We'll just leave it n. Bring down the t. Divide the 18 by the 6. That's t cubed. The entire root. Done. That'll conclude the letter A part. We'll be moving into the letter B part, and we'll have 9.1 done. Let's put a final touch to 9.1. 9.1 is finding roots. We just left letter A, where the index that we were dealing with was even. And we said if the index is even, the radicand had to be a non-negative number. It had to either be a 0 or it had to be a positive number. Now let's finalize it and let's go to letter B. If the index is odd, what does the radicand have to look like in this scenario? If the index is odd, the radicand can be any real number. It can be 0, which it's not going to be for us. It can be positive, or it can be negative. So if the index of the radical expression is odd, the radicand can be any real number. It can be a positive, or it can be a negative. Next statement. The odd root of a positive number, the odd root of a positive radicand will always be positive, and the odd root of a negative radicand will always be negative. So if the index is odd, the radicand can either be a positive number or a negative number, and it will satisfy over the set of real numbers. Let's take a look at number 1. The cubed root of 27. Now, I know many of you would look at that and say, well, I believe that root is 3, and you're absolutely right. But if somebody needed a little bit of further work to be shown, I'm going to once again do this. I'm going to bring down that radical symbol and put that index of 3 in there. And I'm going to prime factor 27 so nobody is in doubt of the answer. If you don't need to use prime factorization for it, don't. But I'm going to institute it so you can just see. We can do 3. It'll go 9 times. We can do a 3 again, and it'll go 3. We stop there because he's prime. 1, 2, 3. 3 to the third. This is a perfect third power or a perfect cube. The exponent is divisible by the index. Bring down the 3. Divide the exponent by the index. We'll get 3 to the first, or simply 3. So even on this one, if we can take a look at this rule number 1 that we're working with right here, just to see it again. If a radical expression represents a rational number, this radical expression represents a rational number because 27 is a perfect cube. It matches that index. Then we're going to write the rational number in place of the radical. We're going to write 3 because it was a perfect cube. Index is odd. He happened to be positive. He can. Let's go to 2. Once again, the cubed root, the index is odd. The radicand can be any sign number. -8, x to the 6th, y to the 3rd, z to the 15th. If the index is odd, the sign of the radicand can be any real number. Positive or negative. He's negative, he's defined. He wouldn't be defined if the index was even, but he's defined if the exponent is odd. I'm going to bring this down again so there's no doubt. I'm going to prime factor 8. Not that I would need to, but I'm going to prime factor it. I'm going to make a little parenthesis here first and get it ready, and I'm going to put that negative sign in. If we prime factor 8, we can do it by a 2. That would come down to a 4. We can do it by 2. It would become a 2. The prime factorization of 8 is 2 cubed, or 2 to the 3rd. I'm going to put that in the house with that negative sign. That is -8. Bring down that x to the 6th, y cubed, z to the 15th. Let's divide about 4 times. Bring down that base of negative 2. Take its exponent, divide it by the index of 3. 3 divided by 3, a negative 2 to the first, or just simply negative 2. Bring down the x. 6 divided by 3, x squared. Bring down the y. 3 divided by 3, y. Y to the first, it's y. Bring down the z. 15 divided by 3 to the 5th, done. So this radical expression, it represented a rational number. We write the rational number in place of the radical. Let's go to number 3. We'll change the index. The 5th root, odd, any sign. Let's see if this overall radical expression is going to represent a rational number. He will be if this radicand represents a perfect 5th power. Why did I say a perfect 5th power? Because the index is 5. Well, the 8 to the 10th is a perfect 5th power because the exponent of 10 is evenly divisible by 5. B to the 30th is a perfect 5th because its exponent is evenly divisible by 5. What about him? Well, he's too big. So let's use prime factorization and get it down so that we can comprehend it in a better way. Put that index there. I'm going to make another parenthesis and I'm going to institute that negative sign. Let's prime factor 243. We can't prime factor that by 2 because he's odd. But let's check 3. 2 plus 4 is 6. 6 plus 3 is 9. 3 divides into 9 evenly. 3 will divide into 243. 3 will go into 243, 81. We can do it by 3 again. 3 will divide into 81, 27. Again. And again. 3 to the 5th, negative 3 to the 5th, A to the 10th, B to the 30th, actually that 5 right there, we'll put it on the outside. That's where it truly belongs. Bring down that base of negative 3 and divide that 5 by 5 and we'll get 1, or just simply leave it negative 3. A, 10 divided by 5, A squared. B, bring it down, 30 divided by 5, B to the 6th, done. I think prime factorization can help. That's why we're sharing it. Okay, one final one. And I'll kind of make a culminating statement right here as we leave this section. The 5th root. We'll stick a negative sign on the outside. 32. C to the 35th. D to the 10th. I'm going to bring down that negative sign. The the radical index of 5. I'm going to take 32 and prime factor it so we don't have to worry about what our result is going to be. We can do 2, 16. We can do 2, 8. We can do 2, 4. And we can do a final 2, and that gives 2. 1, 2, 3, 4, 5. 2 to the 5th. C to the 35th. D to the 10th. Bring that negative sign down. That's actually an opposite sign, or a -1. -1 times that result is going to be negative. So just bring down that negative sign. Bring down that base of 2. 5 divided by 5 is 1, so we'll just leave it 2. Bring down the C. 35 divided by 5 is to the 7th. Bring down the D. 10 divided by 5 is to the 2nd. The entire answer, -2, C to the 7th, D to the 2nd. Now in summary, rule number 1 in evaluating or simplifying radicals. Rule number 1. If a radical expression represents a rational number, we write the rational number in place of the radical. That's what appeared with letter A, and that's what appeared with letter B. What was true about all of those? Every single one of the radicals was a perfect nth power. When I say it was a perfect nth power, I meant that it was either a perfect square, a perfect third power or a perfect cube, a perfect fourth, a perfect fifth, or a perfect sixth. Now, I would venture to say that some of you might be thinking right now, what if the radical expression doesn't represent a rational number? What if it doesn't represent a rational? Well, that's what we're going to be dealing with as we move forward into Chapter 9 and we get into 9.2. One little final thing. What we're going to be dealing with in the rest of the way in Chapter 9, we're going to find out that radicals can be multiplied together, they can be divided, they can be added, and they can be subtracted from one another. Just like polynomials can be added, subtracted, multiplied, and divide, same thing happens with radicals. So we'll be moving into 9.2.